Okay, this lesson is about related rates and time rate problems. So that at the end of this lesson, you should be able to present a detailed solution to a related rate problem or a time rate problem. Okay, rate of change problem can be in terms of how fast a quantity is changing with respect to one of its independent variable, or it can be how fast a quantity is changing with respect to time. So this discussion will be on the interpretation of the derivative, say dy dx, as an instantaneous rate of change of y with respect to x. Again, here are some steps suggested for us to be able to solve time rate problems. I will just be illustrating how to make use of them in solving some applications. Okay, to illustrate how to solve related rate or time rate problems, let us consider this particular item. That a 17-foot ladder is leaning against a wall. If the bottom of the ladder is pulled along the ground away from the wall at a constant rate of 5 feet per second, how fast will the top of the ladder be moving down the wall when it is 8 feet above the ground? So again, the first step is for you to draw some illustration, and our illustration is done on the assumption that the wall is perpendicular to the ground. So here is the ladder. The top end is leaning against the wall with the lower end on the ground. Okay, so we will be representing the distance of the lower end of the ladder from the wall as x, and the upper end distance from the ground as y. Now, as we pull away this end in this direction, the quantity x would be increasing, but pulling this lower end away from the wall this direction would mean that this upper end would be sliding down, and hence the quantity y would be decreasing over time. However, at any time t, x, y, and 17 are associated with one another by means of the Pythagorean theorem, and therefore we end up with x squared plus y squared is equal to the square of 17. This is our working equation that will give us a way to determine how fast the top end would be moving down the wall at the instant that it is 8 feet above the ground. So let us analyze the given data. As we pull this end away from the wall, as we mentioned earlier, this dimension x or distance x would be increasing, and that the rate at which it is increasing is the same rate that this end is being pulled away in this direction, and therefore dx dt is 5 feet per second. Now, as we pull away the lower end, the upper end slides down. At what rate, we do not know, and that we want to know how fast it is sliding down at the instant that the upper end is 8 feet above the ground. So on the basis of this working equation, what we do next would be to apply implicit differentiation, differentiating this with respect to time t, ending up with this expression of 2x dx dt plus 2y dy dt equal to 0, and giving us dy dt expression in terms of negative x over y times dx dt. Now, in determining what dy dt is, we need data for x, y, as well as dx dt. Now, we are given dx dt to be 5 feet per second. We are given the particular instant where we want dy dt determined, and that is y equal to 8. What we do not know is x, but we can compute that using the Pythagorean theorem, that at y equal to 8, x will be equal to 15. And therefore, when we substitute in the values, in this particular expression with x equal to 15, y equal to 8, and dx dt equal to 5 feet per second, we end up with dy dt equal to negative 15 over 8 times 5, or we have negative 9.375. Now, please take note that Instantaneous rate of change values can be positive or negative. It would be positive if the quantity is increasing in value over time, but would be negative when it is decreasing in value over time. Okay, for our second example, let us consider this problem. Water is flowing into a conical reservoir 20 feet deep and 10 feet across the top at the rate of 15 cubic feet per minute. Now find how fast is the surface rising when the water is 8 feet deep. Okay, again, we work on some illustration. So we have the conical tank there, or the conical reservoir, 20 feet deep and 10 feet across the top, at the top. So the radius of the top of the vessel will be 5 feet. Okay, so what is happening is that we are pouring in water in this particular reservoir at this rate of 15 cubic feet per minute. Now, look at what happens when we start pouring in water at this rate. As we pour in water into this tank, the volume of water that is contained in the tank would be changing with respect to time. And as the volume of water in the tank increases, the depth of the water in the tank would vary or is changing over time, as well as the radius of this circular surface here. So the amount of water that is inside the tank would vary with respect to time, and it is changing at the rate of 15 cubic feet per minute. As we pour in water, depth would be increasing, as well as this radius. Okay, so this problem is concerned about how fast is the surface of the water rising. Now remember, if we pour in water in the tank, this upper portion here representing the surface of the water would also be going up over time. So how fast the surface is rising would be as fast as the depth is increasing. Okay, so at this point we work on the relationship between R and H, and again we will be making use of a planar graph obtained by looking at the cross section of this figure. So again, you pass or you cut this through its center and come up with an illustration like this. Okay, so the cross section of the conical tank would just be the triangle, and that over here would be the water, and the depth of water at any time t is given by h, and the radius of the circular surface will be r. The tank is 20 feet deep with base radius at the top, not base radius, but radius of the upper portion, which is just a circle, is 5. So with this, we will be able to set up the relationship of R and H again using ratio of sides of similar triangles. So working now on the solution to this problem using the variables t, r, and h as defined in this particular slide, we would like to determine dH dt when the water is 8 feet deep. Now we start with defining the function for the volume of water in the tank, and that will just be in terms of the volume of a cone given by 1/3 base area times height, or we have 1/3 by r squared h. Okay, now please take note that earlier, using the flattened view of the figure, we would be able to work out this relationship using a ratio of corresponding sides of similar triangles. So we will have 5/20 equal to r over h, or r would be h over 4. Using this in place here, we can express v function of h only. Okay, why do we have to substitute out r? It's because what we want eventually is dH dt. So we need to express v function of h only. So we have this now as our working equation. The basis for differentiating with respect to time. So we differentiate volume with respect to time, and that will give us pi over 16 h squared times dH dt. So solving now for dH dt, when h is 8, we will have it equal to 16 times dV dt divided by pi h squared, or we have 16 times 15 divided by pi times the square of 8, giving us 15 over 4 pi feet per minute. Okay, so please take note that the instantaneous rate of change here is positive, indicating that water is rising and that water level or the water surface likewise would be rising. Okay, to recap, it is the interpretation of the derivative as an instantaneous rate of change of a variable with respect to another that was applied here in solving rate of change problems, and that when the independent variable is time t, then the rate of change problem is referred to as a time rate problem. Okay, so I'll see you in the next lesson.